Thank you everybody for being here. So we're going to shift gear here a little bit and discuss how these numerical simulations can be used for a different purpose, which is to simulate seismic and geodetic data observed, collected in the field. And what I'm going to discuss today is how we can augment, modify and augment the boundary integral method to include the effect of viscoelastic deformation in the ductal domains of the lower crust and upper mantle, for example. So we have, in fact, many examples of the seismic cycle affecting the flow of the asthenosphere or the lower crust through the observations of the post-seismic deformation that follows large earthquakes. And there are literally a lot of these observations that have been made in the last few decades, particularly with the GPS data and later INSAR that have documented how the lower crust or asthenosphere readjust to the rapid stress change imposed by an earthquake, and then accelerate the flow for several decades. And so I invite you to look at several review papers that have been done on this subject, for example, by Roland Bergman and Dressen, or by more recently by Fred Politz. But I want to show you still one such example from the largest strike-slip earthquake to have ever been recorded, which is the 2012 magnitude 8.6 Indian Ocean earthquake sequence that occurred offshore Sumatra in the Indian Ocean and ruptured several fracture zones in the so-called Wharton Basin. And this earthquake created co-seismic deformation, but also triggered an accelerated viscoelastic flow of the oceanic asthenosphere, which stretched the island of Sumatra for several decades. And that was recorded by a local GPS array that stretches more than 1,000 kilometers, that recorded how the Earth's surface rebounded up and down and stretched horizontally during this time scale. And so that's an example how earthquakes actually modify the flow of the asthenosphere. But the opposite is also equal, in the sense that the viscoelastic flow of the asthenosphere participates in the loading of faults. And in fact, that's completely embedded in this concept of plate tectonics, where we have semi-rigid plates that float above a viscous asthenosphere, a viscoelastic asthenosphere that allows continental drift, seafloor spreading, and the relative motion between tectonic plates. And so this viscoelastic deformation concentrates at tectonic plate boundaries, where the interseismic strain rates are the largest. And here we have an example of a spatial distribution of this strain rate underneath the San Andreas fault system in California that concentrates below the San Andreas fault in central and northern California, and exhibits widely distributed deformation in southern California, reflecting how the San Andreas fault system, in fact, engages many different faults, from the Newport, Inglewood, Rose Canyon fault on the west side to the San Jacinto, the Elsinore, and the San Andreas fault on the east side. And so we now have increasing high resolution picture of how there is a full mechanical coupling between earthquake cycles and viscoelastic flow in the asthenosphere and lower crust. And so we want to be able to connect the two in dynamic simulations that resolve this mechanical coupling at different timescales. So how to do this is the purpose of this presentation. So we want an integrated model of the lithosphere that incorporates regions that flow in a distributed manner in the ductal domains of the upper mantle and lithosphere, connecting to very extremely localized deformation along faults. An example of this, which is kind of in the back of my mind as I explore these things, is how to model subduction zones. So subduction zones are the perfect example of this because they combine all different types of seismicity, normal, reversed, transform, along different structures, and they exhibit a lot of lateral variation in physical properties such as temperature, fluid content, and faults. Many subduction zones are in fact complemented by very long continental transform in the case of oblique subduction. And so Sumatra, Japan, the North Anatolian Fault, etc., are examples where a continental transforms combined with subduction megathrust to accommodate plate boundary motion. And so one strategy to model this kind of complex tectonic setting is to augment the boundary integral method to combine surface elements that represent highly localized deformation. And that's the type of simulation that we've seen this morning, for example, and combine this with volume elements that represent the accumulation of plastic strain in the ductal domains, primarily by viscoelastic deformation, but also poroelastic or thermoelastic deformation. So surface elements can take the form of rectangle patches or triangle patches. Volume elements can take the form of cuboids, so that's an extension of a rectangle, or tetrahedra, polyhedra, spheroidal volumes, you name it, where the deformation can be prescribed. By meshing the domain, the oceanic lithosphere, the mantle wedge, lower crust, we can then prescribe where the viscoelastic flow will happen and couple it to the seismic cycle. So the integral method is simply the natural extension of the boundary integral method, where instead of having simply boundaries in the domain, we also have volumetric deformation. And in this context, the change of traction on a fault plane anywhere is caused, as in the boundary integral method, by the slip that happens anywhere else on the fault or even on other faults. But the change of traction that control the evolution of sliding also come from the stress induced by viscoelastic deformation. So an equation that describes this type of coupling is the first one on this slide, where you have the rate of traction in any direction, results from the stress interactions due to the fault slip. So that's the first double integral over fault areas, and attractions that come from strain rates, distributed strain rate in the surrounding rocks. And that's a triple integral representing a volume integral over the viscoelastic ductal domain. Added to this, a so-called radiation damping term that describes the effect of stress reduction by the radiation of seismic waves away from faults. So in this context, we are going to describe the quasi-dynamic integral method, where the radiation of seismic waves is simply approximated. Then the effect of earthquakes on the viscoelastic flow, the other direction of coupling, can be represented by an evolution equation as well, where the stress in the volumes is caused by the motion of faults, so it's proportional to sliding velocities, but also relaxed and modulated by the internal dynamics of viscoelastic deformation that may strain for different reasons, and grain size evolution, temperature evolution, et cetera, et cetera. So there is a surface integral and a volume integral. And the good news is that these stress interaction kernels that multiply velocity or strain rate are readily available in closed form for a half space. These are in fact elastic kernels for point sources. So we can, in principle, conduct these calculations readily. So in fact, we can go one step further and discretize the domain with finite surface elements and finite volume elements instead of relying on point sources. And the stress interaction kernels for finite fault patches is readily available for rectangle patches, triangle patches, in the equations of Okada, 1992, or Niku et al., 2015. And the deformation, the stress and deformation caused by volume element is also readily available for cuboids and tetrahedra volume elements. So as a result, we can turn these integral equations into an algebraic equation that simply relates the contribution of different mesh elements, surface elements, volume elements, into the tractions and the stress components. So this equation simplified to these two ones, now fully coupled. Stress change is a linear combination of slip on the fault and a linear combination of the strain rate on different volume elements. And this change of stress, it follows the same structure. It's a linear combination of sliding velocity of faults and strain rate in volume elements. The only difference is that these kernels are different for stress and traction. In these equations, we can impose a background rate of sliding, so that's the velocity V naught, or a background strain rate for volume elements, and that's the strain rate epsilon dot naught. So that's kind of interesting because a volume element can strain in 6 independent components of strain, and that is caused by 6 different components of stress. And so the stress interactions for a single element already represent a 6 by 6 matrix of stress interactions relating stress and strain rates. And so in general, the stress interaction matrix for volume elements is this combination of large matrices describing the stress interaction from different components of stress to different components of strain in space. So it's a full matrix. It's a lot of calculations to obtain these matrices, but they can be computed once and for all, and then used and recycled in a single simulation to perform time stepping, and only simple matrix vector multiplications are needed to time forward in the simulations. So I'm going to show a simple example with in plane strain. So it's a 2-dimensional approximation to give you an idea of the potential of the approach. And on the right, I show examples of these calculations of stress in the volume. So every row here is the stress component, and every column is a source of that stress. So these triangle elements in 2D will deform, they will stretch in the horizontal direction, the vertical direction, or in a shear component. And that will induce stresses in the same stress component, but also the two others in plane strain. So we have these 3 by 3 strain rate to stress interaction matrices to take into account. So we can calculate the stress interaction efficiently with closed form solutions that represent the effect of deforming volume elements, whether they are rectangular or they are triangular. And the result is a very efficient method for time stepping. So an application of this that I'd like to describe in more details is to simulate the interaction between slip on a megathrust at a subduction zone and viscoelastic flow in the underlying oceanic lithosphere or in the mantle wedge. And this is the type of calculation that is relevant for the Tohoku 2011 Tohoku megaquake in Japan. So a little bit of tectonic context here. We are at the Japan Trench, and imagine a world before Tohoku, where historical seismicity only indicated quite frequent magnitude 7 earthquakes on the down dip extension of the seismogenic zone or at intermediate depths above. And so the examples of this are the 1978 and 2005 events close to the coast, and the 1981 and 2003 events a little bit up dip. And so in this context, we want to understand what governed the succession of these relatively small partial ruptures of the megathrust that eventually culminate in megaquakes that rupture the entire seismogenic zone all the way to the trench. So we're going to use seismic cycle simulations to kind of address this question, and assuming a two-dimensional approximation. So to do this, we implement the integral method for representative cross-section. So you can see in this diagram on the top that we have a megathrust that extends from the surface to the so-called cold nose of the subduction zone. This is a place where the temperature advected by the downgoing slab keeps the domain brittle. But we complement this with a triangular mesh in the mantle wedge and the oceanic asthenosphere that captures the viscoelastic behavior of these domains. So the fault is governed by a rate and state-dependent friction law, and the viscoelastic domains are controlled by a rheology that includes dislocation creep. It's a nonlinear stress-strain rate relationship, but also includes a transient strain, which is an accelerated phase that happens with any stress perturbation. And the model produces, many thousands of years of deformation, and that includes cycles of what we call seismic supercycles. So many partial ruptures of the megathrust, followed eventually by a full rupture of the megathrust in a giant megaquake of magnitude 9. Okay, and so that exhibits a lot of variability because of the change in fault geometry, the coupling with the viscoelastic layer, and the relative, unstable nature of the friction laws. So we explain the succession of small and partial ruptures, partial and full ruptures, by the unstable nature of the fault in the so-called determinist chaos regime that spontaneously produces this kind of behavior. So the model can then be probed. It produces, in this case, 30,000 years of simulation for every model considered. And so in this catalog of synthetic earthquakes, we can draw giant earthquakes and compare them in a statistical sense to the one observed at Tohoku in the Miyagi segment of the Japan Trench. And so the largest of these synthetic megaquakes was produced, in fact, more slip than was observed during Tohoku, reaching up to 60 meters of slip near the trench. But others are more immediately comparable with the observations. And so you can see on the second column, on the second row of this figure here on the right, the distribution of slip for the largest event in the model in black, and one that is more Tohoku-like in red, and how it compares with slip inversions from geodetic data, including seafloor geodesy, with this dashed line. So these seismic cycle simulations can basically reproduce the slip that happened during the Tohoku earthquake without invoking strong weakening mechanisms or other complicated fault frictional mechanism. In addition, the model can be used to predict surface deformation, horizontal and vertical, and that can also be compared with observations. So, and these are the next two rows in this figure. First one shows the horizontal displacement. You can see that it goes through the observations on land quite well. And then the model continues to predict the deformation offshore, and that goes through the scatter of observations from seafloor geodesy. This is for horizontal displacement, and you can see that there's more deformation even closer to the trench than there is in the seafloor geodetic data. The red model also predicts the vertical displacement quite well, with both onshore and offshore. So we can then, because the model includes viscoelastic deformation, we can continue the simulation and inspect what happens in the post-seismic period, where the deformation continues, albeit at a reduced rate for several decades. And we can also compare this with observations. So one thing that was observed after the Tohoku earthquake is the so-called retrograde motion of the seafloor after the earthquake. What do we mean by retrograde? Well, the hanging wall of a megathrust should move seaward, and for a few years, the hanging wall of the megathrust was actually moving landward, as if it was opposite side of the trench, and so that was a little bit puzzling. And what this model shows is that we can explain this retrograde motion by deep afterslip, deeper than the seismogenic zone, right? On segments of the megathrust that plunge into the asthenosphere with a higher angle. And so because they have a different deep angle than the shallow section, the surface displacement, the vertical surface displacement that this induces does not align with the trench. And so some near trench area that is in the accretionary prism can in fact move landward. So this is one way that these seismic cycle simulations can help explain puzzling observations in nature. The model also predicts the vertical displacement, which was also observed. And you can see that it's not in great agreement with the observations. And a reason for this is that the simulation actually includes aftershocks that become very difficult to remove from the synthetic data, because the two-dimensional approximation makes them much bigger than they should be in the natural world. And so there's some complexity here in the simulations to parse out what is seismic and aseismic. And you can see that there is also additional deformation on land, and that is due to viscoelastic flow below the volcanic arc, as was shown by Hugh and other in 2014. So one concern, though, is to move from two-dimensional models to three-dimensional ones. And this transition is actually not as trivial as expected. And the reason is that the stress interactions between neighboring volumes and even within individual volumes themselves is more complex than in two dimensions. And so I'm showing you here calculations of how the stress looks like around the deforming tetrahedron volume. And I'm calculating here two different scenarios. One, looking at the stress in any component, say sigma 1,1, due to the strain epsilon 1,1, or the stress 1,3, component 1,3, due to the strain 1,3. You see what I'm saying? So it's self-stress interactions, stress caused by deformation in the same kind of direction. And when that's the case, you can see that inside the deforming volume, the stress is relatively homogeneous. So it's straightforward to decide to pick a value of stress that is representative of the whole volume. But if we start looking at other stress interactions, so for example, the stress in the 1,1 direction, 1,1 component caused by strain in the 2,3 component, the stress is actually heterogeneous, measurably heterogeneous within the deforming volume. And so it becomes difficult to choose a representative value to use in our matrix vector calculations. So the question is how to select a representative value for these cases in 3 dimensions. And some very interesting work by Shi and Meng recently published shows that taking a volume average of the stress within the deforming element actually stabilizes the problem and leads to stable calculations. If not, if we take the central value and defining the center in a tetrahedron is non-unique, leads to unstable calculations that essentially blow up numerically, that they do not converge. So it's a major issue. So to do this, to solve this, we take volume averages of stress within deforming elements. So this is the equation here on the left, where a representative value of stress in any direction caused by anything, whether a distant fault or a distant volume element or even the same one, is simply the average within that volume. So it's a triple integral of stress scaled by the volume of the element. And that can be evaluated numerically using three-dimensional Gauss-Legendre integration or Gauss-Legendre quadrature. So for example, for a tetrahedron ABCD volume element, these corners A, B, C, and D, the stress, the average stress within this volume is simply a linear combination of stress at strategic points within the volumes. It follows this kind of complex summation, which is due to the non-rectilinear geometry. But the weights are simply the weights of Gauss-Legendre quadrature in the -1, 1 interval, and the integration points are the zeros of Legendre polynomials. So we can do this calculation not in closed form, but still very efficiently with double precision arithmetic accuracy. And so it's just as analytic and also very fast. This is the distribution of these weights and nodal points for rectangle, triangular, cuboid, and tetrahedron volumes for different degrees of accuracy of this
okay
of the numerical quadrature. So you can see that they're unevenly distributed for non-rectangular geometry, and we can calculate this at any accuracy possible. In reality, these calculations are very computationally costly because the stress is already resulting from a two-dimensional integral, and then we have to average it over a three-dimensional volume. So there's basically 5 nested integrals to be conducted to find a stress interaction point. So to mitigate this, we reduce the accuracy of the numerical quadrature. We choose the number of points based on the source receiver distance, and we treat the Green's functions very specifically for the real source term and the image. And eventually we can get calculations that are, acceptable, that conducted in an acceptable time. So this leads to numerically efficient, stable calculation of seismic cycle in 3-dimensional viscoelastic media. The key here is 3 dimensions. So I'm going to show you some examples. And can somebody give me an idea of time? I'm not sure how long I have left.
You have about -20 seconds, I think, Sylvain.
-20 seconds. Okay, yeah. So we have examples of simulations on strike-slip fault with cuboids, volume elements. They can predict surface displacement at any arbitrary distance from the model. So that's the advantage of the boundary integral method. We can also do it for thrust faults with tetrahedron volume elements capturing structural complexity in that is realistic. And what else? And again, explain the deformation that happens in the surface. And the key advantage of the boundary and volume integral method is that we can distinguish the deformation caused by faulting or viscoelastic flow, because it's actually the deformation is a linear combination of both. So it's very convenient to explore data sets and fit data better. So I will stop here. I've described the integral method that it augments the boundary integral method with volume elements, and it's very useful to calculate distributed deformation at large scales including viscoelastic and poroelastic deformation. We can now obtain realistic simulations with realistic features like structural complexity. So thank you for your time, and I will see you later for some questions.